We are now concentrating on chapter 6. The title of the chapter 6 was the fundamental theorems of bounded linear operators. In module 1, we have shown a result on open mapping theorem and proof was already been shown, and also we have got some results in connection with open mapping theorem. Now, we start module 2 of chapter 6. The chapter 6 starts with closed graph theorem. So, it is a matter of fact that all linear operators in practical importance are bounded. We have already seen that differential operators are unbounded linear operators. In quantum mechanics and in many other applications, one need unbounded linear operator. So, the linear operators which we use are called closed linear operators. So, the module starts with the introduction of closed linear operator and with the closed graph theorem, under which a linear operator on a Banach space is bounded. Now, we start with module 2 of this chapter 6. This module starts with a theorem, namely closed graph theorem. The closed graph theorem is derived directly from the open mapping theorem. Still, it is considered sometimes to be more useful than the open mapping theorem. It can be observed that given linear spaces capital X and capital Y over the field capital F, the Cartesian product x cross y is again a linear space over capital F under the algebraic operations given by x1 y1 plus x2 y2 is equal to x1 plus x2 comma y1 plus y2 for all x1 y1 comma x2 y2 belonging to x cross y, that is sum is taken as coordinate wise, and number 2 lambda xy is equal to lambda x comma lambda y for all scalars lambda taken from capital F and for all xy belonging to x cross y. If moreover capital X and capital Y are nonlinear spaces, then x cross y is again a nonlinear space with respect to the norm defined by norm x comma y is equal to norm x plus norm y, where x comma y belonging to x cross y. Also, we can have two other norms on x cross y given by norm x comma y is equal to norm x to the power p plus norm of y to the power p whole to the power 1 by p, where p are x comma y belonging to x cross y, and number 3 norm of x comma y is equal to max of the set norm of x comma norm of y, where x comma y belonging to x cross y, that is pair x comma y belonging to x cross y. It is to be noticed that if x and y are Banach spaces, then x cross y is also a Banach space with respect to any one of the above norms. We here consider the norm defined by 1. Indeed, if Zn with Zn equal to pair xn comma yn is a Cauchy sequence in x cross y, then sequence xn and sequence yn are Cauchy sequences respectively in x and y. Since norm of Zn minus Zm is less or equals to norm of xn minus xm plus norm of yn minus ym, this follows by norm axiom 3, and which goes to 0 as n comma m tends to infinity. As capital X and capital Y are complete, let xn goes to x in capital X and yn goes to y in y as n tends to infinity, and so Zn converges to z as n tends to infinity, where z is equal to pair x comma y belongs to x cross y. The graph denoted by Gt of a mapping T x to y is defined by Gt is equal to x comma Tx, where x belonging to x, Now GT is a subset of x cross y. So in this regard we get a theorem. Let capital X and capital Y be two Banach spaces over the same field of scalars, and let T is a mapping from X to Y be linear. Then T is continuous if and only if graph of T, that is GT, is a closed subspace in X cross Y. The proof: clearly if T is a linear, then GT is a subspace of X cross Y. Now suppose that T is continuous and let xy belongs to GT bar. So there exists a sequence xn comma txn, which is again a subset of GT, that is graph of T, such that xn comma txn goes to xy as n tends to infinity. This implies norm pair xn comma txn minus pair x comma y tends to 0 as n tends to infinity, which implies that norm xn minus x plus norm txn minus y tends to 0 as n tends to infinity with respect to the norm defined as above, which again implies that norm xn minus x tends to 0 and norm of txn minus y tends to 0 as n tends to infinity. So which implies that xn goes to x and txn goes to y as n tends to infinity. Since t is continuous and xn goes to x as n tends to infinity, we have txn goes to tx by the property of continuity of t. That is, txn goes to tx as n tends to infinity. So tx is equal to y. So pair x comma y is equal to pair x comma tx, which is again an element of graph of t. Hence GT is closed. We have started with x comma y belongs to GT bar, and we have shown that x comma y belongs to GT. So GT bar is a subset of GT. Automatically GT is a subset of GT bar. So GT is equal to GT bar, and consequently GT is closed. Conversely, let GT be a closed subspace in X cross Y. So GT is complete. Hence GT is a Banach subspace of X cross Y. Let us define a map F from GT to X by F pair x comma tx is equal to x, where x comma tx belongs to GT and x belongs to capital X. Clearly F is bijective, that is F is injective and surjective, and F is also linear. Also norm F of pair x comma tx is equal to norm of x by the definition of small f, which is again less or equals to norm x plus norm tx, because norm of tx is always greater or equals to 0. So norm of x plus norm of tx is less or equals to norm pair x comma tx. So f is bounded, that is f is continuous. We know that if a linear operator is bounded, then it is continuous and vice versa. So f inverse is a mapping from x to GT, and f inverse exists, and f inverse is a bounded linear mapping from x to GT. Now for x belonging to capital X, norm of tx less or equals to norm tx plus norm of x, because norm of x is greater or equals to 0. Thus norm of tx plus norm of x is less or equals to norm pair x comma tx, which is again equals to norm f inverse x. Since f inverse is bounded, so norm of f inverse x is less or equals to norm of f inverse into norm of x. So t is bounded, because we have calculated that norm of tx less or equals to norm of f inverse into norm of x. As norm of f inverse is bounded, so norm of tx is bounded, and hence t is bounded, that is t is continuous on capital X.
a linear operator T mapping from x to y where capital X and capital Y are two nonlinear spaces over the same field of scalars is called a closed linear operator if its graph, that is GT, is equal to the collection of all elements pairwise taken, that is x comma y belongs to x cross y such that y is equal to Tx and x belongs to capital X, is a closed set in a nonlinear space x cross y with respect to the norm defined by norm pair x comma y is equal to norm of x plus norm of y, where x y is an element of x cross y. Let capital X and capital Y be two Banach spaces and let T x to y be a closed linear operator, then T is automatically a bounded linear operator. The proof is simply analog proof of the previous theorem. First we show that x cross y with respect to the norm defined by norm pair x comma y is equal to norm x plus norm y, as x y is an element of x cross y, where x cross y is a Banach space. Let sequence Zn where Zn is equal to pair xn comma yn be a Cauchy sequence in x cross y. Then norm of Zn minus Zm is less or equals to norm of xn minus xm plus norm of yn minus ym, follows by triangle inequality and is given by norm axiom 3. Thus, norm of xn minus xm less or equals to norm of Zn minus Zm, and we have assumed that Zn is a Cauchy sequence in x cross y. So, Zn minus Zm with norm tends to 0 as Nm tends to infinity. So, norm of xn minus xm tends to 0 as Nm comma tends to infinity, showing that xn is a Cauchy sequence in x. Since capital X is complete, let limit of n xn is equal to x belonging to capital X. That means xn converges to an element x belongs to capital X as x is complete, and similarly let limit n tends to infinity yn is equal to y belonging to capital Y. These together imply that limit of n Zn is equal to z is equal to pair x comma y belongs to x cross y, that is Zn converges to z where z is equal to pair x comma y which is an element of x cross y. Thus, we see that x cross y is a Banach space. Now, graph of T, that is Gt, being a closed set in x cross y, it follows that Gt is complete because x cross y is a Banach space, and we know that closed subset of a complete metric space is again a complete metric space. Define a mapping f from Gt to x by f pair x comma Tx is equal to x belonging to x, then f is a linear operator over Gt. Now, norm of f of x comma Tx is equal to norm of x, which is again less or equals to norm x plus norm of Tx is equal to norm of pair x comma Tx, implying that f is bounded. Also, f is bijective. Hence, f inverse x to Gt is a mapping given by x goes to x comma Tx, where x is an element of capital X. Now, we shall show that f is to be bounded. Hence, there is a positive constant k such that norm pair x comma Tx less or equals to k into norm of x for x belonging to capital X. Thus, norm of Tx less or equals to norm of Tx plus norm of x, as norm of x is always positive, and which is again equal to norm x comma Tx, which is again less or equals to k into norm of x, implying that T is bounded. So, the above theorem gives the following useful criterion which express a property that is often taken as a definition of closeness of a linear operator. Now, we now put a definition of a closed linear operator, and this definition can be obtained by a theorem. Let Tx to y be a linear operator where capital X and capital Y are non-linear spaces over the same field of scalars capital F. Then T is closed if and only if it has the following property, that is, if xn goes to x as n tends to infinity, where sequence xn belongs to capital X and Txn goes to y as n tends to infinity, then x belongs to capital X and Tx is equal to y. Now we are going to prove of this theorem. We assume that T is closed and hence Gt is a closed subspace of the non-linear space x cross y with the norm, where we take the norm given by norm pair x comma y is equal to norm x plus norm y, where pair x y is taken from x cross y. Let xn be a sequence in capital X such that xn goes to x as n tends to infinity and Txn goes to y as n tends to infinity. Then norm pair xn comma Txn minus pair x comma y is equal to norm xn minus x comma Txn minus y is equal to norm xn minus x plus norm Txn minus y tends to 0 as n tends to infinity, implying that limit n tends to infinity pair xn comma Txn is equal to xy in x cross y with the given norm. Hence x comma y belongs to Gt bar, but Gt being closed, so xy belongs to Gt. Hence it follows that x belongs to x and Tx is equal to y by the definition of graph of the operator T. Conversely, let x comma y be a limit point of Gt, that means x comma y is taken from Gt bar. Thus, there exists a sequence pair xn comma Txn in Gt such that limit n tends to infinity pair xn comma Txn is equal to x comma y, which implies that limit n tends to infinity norm of xn minus x comma Txn minus y, which is equal to 0, which again implies that norm of xn minus x plus norm of Txn minus y goes to 0 as n tends to infinity, which implies that limit n tends to infinity xn is equal to x and limit n tends to infinity Txn is equal to y. So by hypothesis it follows that x belonging to capital X and Tx is equal to y. Hence x comma y belongs to Gt and consequently Gt is closed. So T is a closed linear operator. Now we get a theorem. Let capital X and capital Y are nonlinear spaces over the same field of scalars capital F. Suppose that Tx to y be a linear operator, then T is closed if and only if graph of the operator T be a closed set in x cross y with respect to the given norm in x cross y, where the norm in x cross y is given by norm pair x comma y is equal to norm x plus norm of y, where xy belongs to x cross y. The proof runs as follows. Suppose that T is closed. Let x comma y belongs to Gt bar. So there exists a sequence pair xn comma Txn belonging to Gt, where sequence xn is an element of x such that pair xn comma Txn goes to xy as n tends to infinity, that is norm pair xn comma Txn minus pair x comma y goes to 0 as n tends to infinity, which implies that norm xn minus x comma Txn minus y goes to 0 as n tends to infinity, which again implies that norm of xn minus x plus norm of Txn minus y goes to 0 as n tends to infinity. So norm of xn minus x tends to 0 and norm of Txn minus y tends to 0 as n tends to infinity, which implies that xn goes to x as n tends to infinity and Txn goes to y as n tends to infinity. Since T is closed, we get x belonging to capital X and Tx is equal to y. So x comma y is equal to x comma Tx, which is an element of graph of the operator t, that is x comma tx belongs to gt, and so x comma y belongs to gt, and hence gt bar is a subset of gt. Also it is obvious that gt is a subset of gt bar, and consequently gt is equal to gt bar, so gt is closed. Conversely, suppose that gt be closed in product space x cross y. Let sequence xn is an element of x be such that xn goes to x as n tends to infinity and txn goes to y as n tends to infinity. Now pair xn comma txn goes to xy as n tends to infinity, but pair xn comma txn belongs to gt and comma y belongs to gt bar. As gt is closed, we can take gt bar is equal to gt, and so x comma y belongs to gt, and so x comma y is equal to x comma tx, and so y equal to tx, hence t is closed. So in this regard we get a remark, let capital X and Y, that is capital Y, be two non-linear spaces over the same field of scalars capital F, and let T x to y be a linear operator. Suppose that T is a bounded linear operator, then T is automatically closed. The proof runs as follows. Let the sequence xn is taken from capital X such that xn goes to x as n tends to infinity, and txn be a sequence in y such that txn goes to y as n tends to infinity. As capital X is closed, x belonging to capital X, since t is continuous, txn goes to tx as n tends to infinity. We have, since txn goes to y as n tends to infinity and txn goes to tx as n tends to infinity, we get y is equal to tx, because non-linear space is a metric space and it is a T2 space, so the limit is unique. So we must get y equal to tx, and so T is closed.
Now we shall be focused on our main theorem, namely known as closed graph theorem, and our motto is to prove this closed graph theorem.
Now I want to state the statement of the closed graph theorem. Let capital X and capital Y be two Banach spaces over the same field of scalars capital F, and let T x to y be a linear operator. Then T is closed if and only if T is bounded. Note that the converse of the above theorem does not hold in general. For this we give an example. Let capital X is equal to C01, and C01 is the space of all real valued continuous functions over the closed interval 0, 1, and y is equal to C dash 01, the space of all real valued continuous functions which are continuously differentiable over 0, 1, and C01 is equipped with the sup norm. Define T from capital Y to X by Tf is equal to f dashed. We see that capital T is not bounded. We shall now show that capital T is closed. Let sequence Fn is taken from capital Y be such that Fn goes to F as n tends to infinity, and Tfn goes to capital F as n tends to infinity. Since convergence in the norm of C01 is uniform on 0, 1 from Fn dashed goes to F, we have integration 0 to s capital Ft dt is equal to integration 0 to s limit n tends to infinity Fn dash t dt is equal to limit n tends to infinity integration 0 to s Fn dash t dt is equal to limit n tends to infinity within the bracket Fns minus Fn0, which is equal to Fs minus F0. So small fs is equal to F0 plus integration 0 to 1 capital Ft dt, where s is taken from the closed interval 0, 1. This shows that f belonging to capital Y and Tf is equal to capital F, implying that capital T is closed. The definition of closed linear operator can also be stated as follows. Let us take a definition. Let T is a mapping from D to Y, where D is a subset of X, be a linear operator. Then capital T is said to be closed if it satisfies the following property. If sequence xn is taken from capital D such that xn goes to x as n tends to infinity, txn goes to y as n tends to infinity, then x must belongs to D and tx is equal to y. Then x belongs to D and tx is equal to y. Let capital X be a nonlinear space and capital Y be a Banach space over the same field of scalars capital F, and let capital D be a subspace of capital X, and let T is a mapping from D to Y, where D is a subset of X, be a closed and bounded linear operator, then D bar is closed. Now we are going to prove of this theorem. Let X belongs to capital D bar. So there exists a sequence xn taken from D such that xn goes to x as n tends to infinity. So norm of xn minus x goes to 0 as n tends to infinity, and this implies that sequence xn is a Cauchy sequence in capital X. Now norm of txn minus txm is equal to norm txn minus xm by the linearity of t, which is again less or equals to norm t into norm of xn minus xm, which goes to 0 as n comma m tends to infinity. So sequence txn is a Cauchy sequence in capital Y. Since capital Y is complete, txn goes to y, which is an element of capital Y as n tends to infinity. Thus we have xn goes to x and txn goes to y as n tends to infinity. Since t is continuous, txn goes to tx as n tends to infinity. So tx must be equal to y. As t is closed, x belongs to D. We have started with x belongs to D bar and we have obtained x belongs to capital D. So D bar is a subset of D and consequently D equal to D bar, and hence capital D is closed. Now we get another theorem. Let capital X and capital Y be two nonlinear spaces over the same field of scalars capital F, and let T is a mapping from X to Y, which is a closed linear mapping. If its inverse exists, that is if T inverse exists, then T inverse is also a closed linear operator. Now the proof runs as follows. Since capital T is closed, its graph GT, that is the collection of all elements taken pairwise x comma tx, where x is taken from capital X, is closed. Since inverse of T exists, that is T inverse exists for each y belongs to capital Y, there exists x belonging to capital X such that y is equal to Tx. Also T inverse is linear. Since x cross y is a nonlinear space with respect to the norm given by norm pair x comma y is equal to norm x plus norm y for all x belongs to x and for all y belongs to capital Y. Y cross x is also a nonlinear space with respect to the same norm, presuming the norm of x cross y. Now GT is equal to collection of all elements taken pairwise, that is x comma tx, where x belongs to capital X, and which is equal to T inverse y comma y, where y runs from capital Y. As GT is closed, the set pair T inverse y comma y, where y belongs to capital Y, is a closed set. Now consider an mapping x cross y to y cross x given by pair x comma y goes to y comma x, where x belongs to capital X, y belongs to capital Y. This mapping is clearly an isometrically isomorphism of x cross y onto y cross x, as the set, which is the collection of all elements taken pairwise, that is T inverse y comma y, where y runs in y, is closed, and so the set y comma T inverse y, where y is taken from capital Y, and but the set y comma T inverse y, where y is taken from capital Y is the graph of T inverse, so T inverse is closed.
In this module 2 of chapter 6, we have started with an introduction of a closed linear operator and finished with a theorem, closed graph theorem. It is to be noted that among the 4 fundamental theorems in function analysis, we have learnt 2 important theorems, that is open mapping theorem and closed graph theorem. With this discussion, we now finish module 2.